Okay, so today we're going to be looking at a problem that has to deal with a voltaic cell. And in this problem we have three parts. We have identifying the anode and the cathode, we have writing a balanced overall reaction, which in this case we're going to actually write a balanced overall net ionic equation because that's more what we deal with in AP. And we're also going to be finding the potential of this cell under standard conditions. Now, looking at the first question, this really isn't too hard because it's written in a format called cell diagram form. So because of this, we know that aluminum is the anode and lead is the cathode. And we know this because the anode is always going to be on the left and the cathode is always going to be on the right in this cell diagram format, which makes these kinds of problems really easy if they give it to you like this. Okay, so the next question is the balanced overall reaction. Now, keep in mind that we know that aluminum is the anode and that lead is the cathode. And actually, by looking at this format, we can tell automatically that we're going to be having, starting with aluminum on this side and then going into Al plus 3. And that's the really convenient part about this. And then we know for our other half reaction at the cathode, we're going to be going from aqueous lead to solid lead. And so we can go ahead and write those out, and that's what the two half reactions are going to look like. Now, what we also need to figure out is which one is oxidation and which one is reduction. And we can tell this because of an ox-red cat. Basically, what this means is that the anode is going to be our oxidation and the cathode is going to be our reduction. So we can go ahead and label those accordingly, and that's really helpful in just making sure that we have the right half reactions. And then now what we can do is we can actually cancel these out, but first we have to balance them to where the electrons will cancel out so that we can get our balanced net ionic. So in this case, we're going to be looking for a common factor of 6, and we're going to multiply those accordingly so to get that. And then we can cancel out our electrons, add the two, what's left over together, and we get our balanced net ionic, which represents our voltaic cell. Okay, so for the last part, we have the potential of this cell under standard conditions. So we're going to actually use the potential list over here. I know it's really tiny, so you guys might not be able to see it, but I'm going to highlight and rewrite the charges we're going to be using. So that's our chart, and those are our two charges. We're going to have these. And now, in this potential list, they give both parts to you in reduction format, but we know that aluminum is actually an oxidation reaction. And we don't only know this because we figured it out earlier, but we also know this because the most positive is going to be your reduction when you're dealing with these. So in that case, our most positive is going to be the lead because it's negative 0.13 instead of negative 1.66. And again, we also know this because of earlier with the anode and the cathode, and the reduction in oxidation and an ox-red cat. So this is just kind of two ways to confirm it that you're going on the right track. Now what you're going to do is you're going to actually flip the reaction they gave you, which we also found earlier, if you just wanted to take it from there. And we also have to flip the charge in this case, though. So you don't mess with the numbers, though. Like I know in our previous slide, we multiplied to get them to balance out so we could get the balanced net ionic equation, but you don't multiply the charges because they're affected by something else. They're not affected by changing that. So then we can go ahead and take our equation and add them together now. So this is our equation. We have E cell equals E reduction plus E oxidation. And so we're going to plug in our numbers now. We're going to have negative 0.13 and positive 1.66. And these are in volts, by the way. All of these E's are going to be in volts. So we can go ahead and add those together, and we get our answer of 1.53 volts. Yay!